Hello everyone, in this video I am going to explain a paper that I selected titled A ConvNet for the 2020s by Liu et al. Presented at CVPR 2022. My name is Randy Wihandika and this video is for an assignment in the Image Information Processing course. Vision Transformers or VIT that was proposed in 2020 has replaced ConvNet or CNN as the dominant backbone architecture in the past few years. VIT is believed to be more accurate, efficient, and scalable than ConvNet, and it can outperform standard ResNet, which was proposed in 2015 by a significant margin. There have been many design choices for ConvNet developed separately, but not collectively. So, the aim of this paper is to gradually modernize ConvNet, particularly ResNet 50 and ResNet 200, by applying different design choices adapted from VIT, and as mentioned in the paper, to test the limits of what a pure ConvNet can achieve. While modernizing the ConvNet in a step-by-step fashion, the computational requirements are preserved for both ResNets, and the proposed version of the ConvNet is called ConvNext. Many steps are taken to modernize the ConvNet, and the steps are grouped in 6 categories: training techniques, macro design, ResNext, inverted bottleneck, large kernel, and micro design. This is the overall chart that shows the improvement in terms of accuracy in each step, and we do it from top to bottom. This chart shows the accuracy for both ResNet 50 and ResNet 200, as well as the computational requirements in gigaflops, marked by the star symbol on the right. The modernized ResNet 50 is called ConvNext T for tiny and is matched against Swing Transformer Tiny, and the modernized ResNet 200 is called ConvNext B for base and is matched against Swing Transformer Base. We begin with the first category, which is the training techniques. Here, the authors use similar training techniques used to train VIT, which are extending the training from 90 epochs to 300 epochs, using the ADAM-W optimizer, using data augmentation techniques, which are mix-up, cut-mix, and rain-augment, and using regularization techniques, which are stochastic erasing and label smoothing. This is the illustration of the mix-up and cut-mix methods, which are probably two most popular image augmentation methods, which combine two images into one, as shown in this figure. The rain-augment technique automatically generates the series of augmentation method to be applied to an image. The random erasing augmentation technique randomly selects a rectangular region in an image and replaces it with some random values. As shown in this figure, the region B can be in any part of the image. By improving the training techniques, the performance was increased by 2.7%, so this model is used as the baseline model. This is where the baseline is on the top of the chart with 78.8% accuracy and 4.1 gigaflops. The second category is the macro design. Here, the authors changed the stage compute ratio, which is the block arrangement in ResNet, as shown in this figure, from 3464 to 3393, and the performance was increased by 0.6% by applying this. The next step is changing the stem or the first layer to patchify. The standard ResNet uses 7 by 7 stride 2 convolution, while VIT uses 14 by 14 or 16 by 16 non-overlapping convolution, and the proposed ConvNext uses 4 by 4 stride 4, which means non-overlapping convolution. This step increases the performance by 0.1%. This is the illustration of the patchify layer in VIT, where the input image is broken down into patches and each patch position is embedded before fed into the encoder. There we are in the chart after applying the macro design techniques. We increased the accuracy by some amount, but the flop is also increased. The third category is mimicking ResNext, which is the improved version of ResNet. The first step is using depthwise convolution that is popularized by the MobileNet. This reduces the network flop but also decreases the accuracy by 1.2% since the capacity of the network is also reduced. The reason of doing this is to keep the flop from going too high because the next step will increase the flop quite significantly. This is the illustration of the depth-wise convolution, which breaks down a convolutional layer into two steps, which are the depth-wise convolution and point-wise convolution. The next step is to increase the network width, or the number of channels, from 64 to 96. This increases the flop as well as the performance by 2.2%. Here we are now in the performance chart. We have improved the performance, but the flop is also increased significantly, so we are going to decrease it in the next steps. The next category is the inverted bottleneck. In the bottleneck technique in ResNet, the number of channels in the middle layer in a block is reduced, as illustrated in this figure, while in inverted bottleneck, we do the opposite, that is, increasing the number of channels of the middle layer. This reduces the flop but increases the performance of ResNet 50 by 0.1% and ResNet 200 by 0.7%. This is another illustration of the bottleneck and inverted bottleneck, where we change the number of the channel in the middle of a block. The inverted bottleneck managed to increase the accuracy and lowering the flop, so this is a very effective step. The next category is using large kernel sizes. The kernel size in Swing Transformer is at least 7 by 7, while the gold standard in ConvNet is 3 by 3, and we want to use larger kernel sizes. However, large kernels are inefficient, so the position of the depth-wise convolution in the block is moved up to improve efficiency. By doing this, the performance is decreased, but we managed to reduce the flop significantly. Different kernel sizes are tried out in this experiment, from 3 by 3 to 11 by 11, and the best performance was obtained using 7 by 7 kernel size, which improved the accuracy by 0.7%. Therefore, 9 by 9 and 11 by 11 kernel sizes are not used further. In the performance chart, we can see that the accuracy is improved while keeping the flop roughly constant, so using large kernel sizes shows a good effect on ConvNet. The last category is the micro design, which includes activation functions and normalizations. The original transformer paper uses ReLU, but more advanced transformers such as BERT, GPT-2, and VIT use Gaussian error linear unit or GELU. However, switching from ReLU to GELU does not change the accuracy on ConvNet. Another difference between ResNet and transformers is that transformers have fewer activation functions. As shown in this figure, the number of activation functions is reduced from 2 ReLUs to only 1 GELU, and the performance is improved quite significantly by 0.7% with this step. Another reduction is in the number of normalization from 2 normalizations to only 1, as shown in this figure, and this step improves the accuracy by 0.1%. As also demonstrated in this figure, the batch normalizations are replaced with layer normalization, and another 0.1% improvement is achieved. The next step is using separate downsampling layers. In ResNet, spatial downsampling is done at the start of each stage using 3 by 3 straight-2 convolution, as shown in this figure. This is then changed to using separate downsampling layers with 2 by 2 straight-2 convolution, and this improves the performance by 0.5%. These final steps in the micro design has significantly improved the accuracy without sacrificing the flop. Now we can see the comparison between the proposed ConvNet and the Swing Transformer, where the ConvNet shows better performance with the same computational requirements at 4.5 gigaflops. For the evaluation, 5 variants of ConvNet are used, which are tiny, small, base, large, and extra large. The differences between these variants are in the number of channels C and blocks B in each stage. The test is image classification, and the performance is measured in terms of top 1 accuracy on ImageNet 1K and ImageNet 22K datasets. This table shows the comparison between ConvNet and other models, RedNet, EfficientNet version 1 and 2, DEIT, and Swim transformers. If we compare the models with the same flop, ConvNet mostly outperforms the others. The only model that outperforms ConvNet is the EfficientNet V2, marked by a star symbol. This table shows the results on the ImageNet 22K dataset. Similarly, it shows that ConvNet's performance is mostly better than other models, including the EfficientNet V2. This also shows the high accuracy achieved by ConvNet XL, indicating that ConvNet is a scalable architecture. The next task for the experiment is object detection and segmentation on the COCO dataset using masked RCNN and cascade masked RCNN. Average precision is used for the performance measurement. This table shows the comparison between Swim transformers and ConvNet as the backbones for the object detection task. ConvNet shows similar or better performance than the Swim transformer and tends to show larger margin on larger scales, for example in ConvNet large and extra large. The final task for the experiment is semantic segmentation on the ADE20K dataset. The metric used is the mean intersection of union, or MIOU. In this table, we can see that ConvNet outperforms the Swim transformer's counterpart in every scale. This figure shows the comparison between ConvNet and transformers trained on both ImageNet 1K and ImageNet 22K. The size of the circles indicates the flop in each model. This figure primarily shows that ConvNet can achieve the same level of scalability as hierarchical vision transformers while being much simpler in design. ConvNet has been considered a good model and has been very common that both TensorFlow and PyTorch include ConvNet in all scales, as well as the pre-trained weights so that we can use it right away. This is the notebook provided by the authors of ConvNet for the image classification task. ConvNet's pre-trained models in all scales have been integrated into the theme library for easier model preparation, as also used in this notebook. Here we are using a pre-trained ConvNet XL model downloaded using the theme library, and it is as easy as calling the create model function. This notebook has been configured for utilizing the GPU provided by Google Colab. Therefore, the pre-trained model is then moved into the configured GPU. We then prepare the transform pipeline for the input image that consists of resizing to 256 by 256, normalizing using the standard ImageNet values and converting into a PyTorch tensor. Then the image is loaded in pillow format, apply the transforms, and move it into the GPU. Another thing to prepare is the class label names. Finally, we can input the image for prediction and get the top K predictions as well as the probabilities. As we can see, the top prediction is X, and it is correct, but the second prediction is also correct, which is an electric refrigerator. As a conclusion, this paper collectively applies various design choices, which were proposed in different studies to improve a plain ConvNet. So in other words, this paper did not really propose any novel idea other than compiling other techniques into one network. However, the proposed ConvNet managed to outperform Swim transformers in many tests while keeping the same computational requirements and has made ConvNet great again. As a further reading, you are suggested to read a paper about ConvNet version 2, that is the successor of the paper explained in this video and was presented in this year's CVPR. These are the references used in this presentation. This is the end of this video about ConvNet. Thank you for watching.